first law of thermodynamics is wonderful news. You can change energy from one form to another as many times as you want to, and the total amount of energy is constant. Energy is conserved. But nature hasn't given us a completely free ride in this regard. The second law of thermodynamics places severe restrictions on how energy can be used, how it can transfer from one form to another. In fact, the second law of thermodynamics tells us that heat has a universal tendency to dissipate. In the last lecture, we looked rather uncritically at the many different ways that energy shifts from one form to another, from kinetic to potential to heat and back and forth and so forth. Recall that example of the roller coaster. The roller coaster starts at the bottom, and you take electrical energy, bringing the roller coaster up and up and up. It gains gravitational potential energy. That changes into kinetic to gravitational potential and back and forth. And ultimately, heat energy in the brakes of the roller coaster as it comes to a stop at the end of your ride. In this lecture, and in the next, my principal objective is to introduce one of the most profound ideas in science, this second law of thermodynamics. In coming to grips with this law, we're going to have to scrutinize nature to see the restrictions on how we can use energy. Such limitations, as outlined in this second law of thermodynamics, have profound consequences for our everyday experience. The British scientist and science commentator C.P. Snow once wrote, quote, "Once or twice I have asked a group of educated people how many of them could describe the second law of thermodynamics. The response was cold. It was also negative. Yet I was asking something which is about the scientific equivalent of, have you ever read a work of Shakespeare? Well, why is this second law of thermodynamics so important? The first law, recall, states that the total amount of energy is constant, but it says nothing about the way that energy can shift from one form to another. In everyday life, we experience many limitations on these energy transfers. For example, a hot bowl of soup. It becomes cooler spontaneously, but a cold bowl of soup never becomes hot spontaneously. A glass of ice water gradually becomes to room temperature and the ice melts, but you never see a glass of water sitting on your table and suddenly ice cubes form in it. Now, either way, energy is conserved, yet one example is commonplace and the other never happens. Another example, gasoline. Gasoline burns in your car to produce heat and exhaust, but you never see exhaust plus heat spontaneously become gasoline. And yet, once again, that wouldn't violate the first law of thermodynamics because the total amount of energy in its different forms would remain constant. Another example, objects fall downward in a gravitational field. You let go of an object, it falls. And it releases heat when it hits the bottom. For example, an asteroid coming in and hitting the Earth would release a tremendous amount of heat. But you never see the other thing. You never see an object falling up and absorbing heat in the process. So objects don't fall up. I want you to imagine playing a favorite videotape backwards. Certain actions and events are going to look silly. They're going to look wrong. They're going to make you laugh. Let me emphasize that all of the events, whether the tape's played forward or backwards, are perfectly consistent with the first law of thermodynamics because energy is conserved either way. So evidently there are restrictions on the flow of energy, and that's why the second law of thermodynamics is required. The most intuitive statement of this second law comes to us courtesy of that British physicist William Thomson, Lord Kelvin, who we met in the last lecture. Kelvin said that heat tends to diffuse. It tends to move out evenly. Heat flows from hot to cold. This statement incorporates two related but different concepts, heat and temperature. And once again, we have to come into this situation of common everyday words like heat and temperature having very specific scientific meaning. Let me tell you about these two words. Heat is a quantity of energy. It's a measurable unit. You can measure the amount of heat an object holds in joules or in calories. 2 kilograms of water at room temperature contain twice the heat energy of 1 kilogram of water. You can take a certain amount of water that's at a certain temperature. There's heat energy here. You can transfer that heat energy into different receptacles, just like that. And now some of the heat energy that was contained in the jar of water, is now contained in 2 glasses. The quantity of heat energy thus depends on the quantity of stuff and the temperature which it's at. And here we come to this word temperature. Temperature is a relative term. 2 objects are at the same temperature if no heat flows spontaneously from one of them to another. 2 objects are at a different temperature if heat does spontaneously flow from the warmer to the cooler object. You measure temperature with a thermometer, and every temperature scale, every thermometer requires 2 reproducible reference points, such as the freezing and the boiling points of water. They're commonly used. You also need to have some physical property that changes. For example, the volume of mercury at a particular temperature. And so you'd build a thermometer which has some mercury at the bottom, and as the mercury gets warmer or cooler, the total amount, the volume of the mercury changes, and so the mercury moves up and down, and that gives you a record of the temperature. So a reproducible physical property is also essential. Lord Kelvin measured the heat energy contained in substances at different temperatures, and he realized that at a very specific temperature, at minus 273.15 degrees centigrade, that's about minus 460 degrees Fahrenheit, you can't get any more heat energy out of any object. And he called that temperature absolute zero, the temperature at which there was no more heat energy that you could pull out of a material. At absolute zero, the kinetic energy of atoms is as close to zero as you can possibly get it. The Kelvin temperature scale, therefore, uses 273.15 and 373.15 as the reference temperatures. That's the freezing and boiling point of water. Note that both the Celsius temperature scale, which we use, and the Kelvin scale are both centigrade scales. That is, there are 100 divisions between freezing and boiling of water. When you start thinking about this difference between heat and temperature, it leads us to another important property, and that's heat capacity. Every material has the capacity to store heat energy, but some materials are much better at this than others. Think about placing a pound of copper and a pound of water on identical burners. I want you to think about this. Which one heats up more quickly? If you put your hand in the water and put your hand on the metal, which one would get burned first? Well, your common experience tells you that the metal gets hotter much faster. And this is because metals are unable to store very much heat energy. But the water is an extremely efficient storer of energy. So water has a very high heat capacity. You have to put a lot of energy before the temperature goes very high. Heat capacity, in fact, is the amount of energy that a substance can hold. And since water is so efficient, this has very important implications for climate and weather. We're going to see that in lecture 41 when I'll talk more about the properties of water. But suffice it to say that water is a very efficient storer of heat energy. A useful measure of heat capacity is called specific heat, yet another term in science. That's the energy that's required to raise the temperature of 1 gram of material by 1 degree centigrade. For water, this energy is defined as 1 calorie. So here we have the definition of a calorie is the energy required to raise 1 gram of water by 1 degree centigrade. By contrast, it only takes 1/10 of a calorie to raise a gram of copper by 1 degree. And so copper has only 1/10 the heat capacity of water. Let's pause for a second and think about the second law of thermodynamics in a different regard. It's in part a statement about the motion of heat, how heat moves. And so we have to say something about the mechanisms, because the law doesn't tell us what these mechanisms of moving heat are. And it turns out there are 3 different ways to move heat. We have conduction, convection, and radiation. And I want to look at these 3 kinds, these common mechanisms that we experience every day. Conduction is the transfer of heat from atom to atom in a solid object. If you take a spoon and you place the spoon in hot water, you notice that very quickly the handle becomes hot too. That's the process of conduction. Heat conducts from one end of the spoon to the other. Conduction is a rather slow process. For example, heat left over from the formation of the Earth, the gravitational formation of the Earth 4.5 billion years ago, is still slowly moving outward by conduction. You've experienced this fact. If you ever gone into a cave on a hot summer day or on a very cold winter day, you find that the cave maintains more or less the same temperature year-round. Even if the cave is only a few tens of feet beneath the surface, the temperature is maintained at a constant level because heat conduction through the rock is relatively slow, and so the cave reaches this equilibrium. Our second way of moving heat is called convection, and that's the transfer of heat through the motion of a whole body of a fluid, either a gas or a liquid. So this includes things like boiling water or ocean currents or the wind. Those are good examples of movement of heat by convection. Your body regulates its temperature in large part by convection. For example, you breathe in air and then breathe it out. And on a cold day, how you see that frost in your breath, well, you're regulating your temperature, at least altering your temperature through breathing. The circulation of your blood also is a kind of convection, and so is sweating. These are all ways of moving heat from one place to another by moving a fluid, a gas, or a liquid. You also, in everyday life, have lots of mechanical convenience, things like fans or hair dryers, and once again, that moves heat, transfers heat, or transfers cooler air from one place to another by just moving a body of air, by blowing it. Now, there's a third way of moving heat. In addition to conduction and convection, we have radiation. That's the transfer of heat in the form of light energy or in heat energy, which moves 186,000 miles per second through a vacuum. You feel that radiant energy from the sun, and that's a way for the sun to transfer its heat energy that's 93 million miles away to us through the vacuum of space. You also feel this kind of radiant energy if you have a space heater or an electric heater or a fireplace, and you feel that warmth, even though you're not necessarily getting direct conduction or convection from that fire. People also radiate heat because you're generally warmer than your surroundings. That's why a crowded auditorium gets hot. In fact, I'm told, and I'm inclined to believe that it's true, that the average person just sitting in a chair radiates the same amount of heat as a 100-watt light bulb. So if you're in an auditorium with 1,000 or 2,000 people, that's a lot of heat being radiated out, and that's why auditoriums can get quite warm if they're not well ventilated. One of the key technologies that we look for is ways to eliminate or reduce this transfer of heat. And humans and nature as well have devised many different ways of reducing the transfer of heat. Animals living in cold climates, for example, use insulation of various sorts. They develop fur. They have feathers. Warm wool clothing, for example, a wool scarf, does a similar sort of thing. Lots of little air pockets. And think about what an object like this would do. The pockets of air that wool form, or the kinds of things that feather and fur would provide in terms of animals. What you're trying to do is cut down the efficiency of heat transfer. And the most efficient heat transfer is by convection. So if you can trap little pockets of air where convection, that cycling of air, can't proceed, then you're restricting the way heat is lost from your body to conduction, which is a much slower process. And that's how insulating materials work in your home, in your clothing, in animals, and so forth. Thermos bottles carry this process a step further by actually having a vacuum barrier. And across the vacuum barrier, you can't even get conduction. The only thing you can do is get radiation. So heat loss is even a slower process, although it still occurs because heat always flows from warmer objects to colder objects, even in the vacuum of space. The second law of thermodynamics is so pervasive, it applies to so many physical situations that there are a number of very different ways of expressing the same fundamental principle. And I want to look at a variety of ways of talking about this second law. We've seen so far that heat flows from hot to cold. But another more subtle statement of the second law is that you can't design an engine that converts heat completely, 100% to work. Think about that statement. Thermodynamics are of immense importance to the designing of steam engines because you're talking about transferring heat. You're talking about using energy in different ways. So in designing steam engines, you're worried about transferring energy in an efficient way. So it's not surprising that some of these insights came from the study of the design and the development of steam engines. I want to tell you about a French military engineer, Nicolas Léonard Sadi Carnot. He came the closest to deriving this second law of thermodynamics from a study of work and heat and the nature of steam engines. Sadi Carnot was born in Paris in 1796. He was the son of Lazare Carnot, who was a famous military tactician, one of Napoleon's great generals and minister of war under Napoleon. The younger Carnot was educated to be a military engineer in his father's footsteps, and he devoted much of his effort to understanding the operation of steam engines, which were just then coming into use and found applications, of course, in the military society. His most important findings were summarized in a little book, a forgotten book, called Reflections on the Motive Power of Fire. It appeared in 1824, but it was completely ignored in his day. It was ignored for almost 20 years. That's long after his death. Carnot died in 1832. I think Carnot's great gift was the ability to see generalizations in very specific situations. For example, working with the mechanics of a steam engine, he could see general principles. This is something that he wrote. Quote, "In order to consider in the most general way the principle of the production of motion by heat, it must be considered independently of any mechanism or any particular agent. It is necessary to establish principles applicable not only to steam engines, but to all imaginable heat engines, whatever the working substance and whatever the method by which it is operated." So we saw steam engines as just a special case of a much more general kind of problem in thermodynamics. Carnot considered two different sides of this relationship between work and heat. On the one hand, he recognized that you can convert work to heat with 100% efficiency. Work can be completely transferred to heat. For example, if you drop an object, if you take a ball and drop it, it has gravitational potential energy. It does work, it lands on the ground, and the work is converted completely to the heat energy in the floor. Now, you may say, well, it doesn't seem like there's very much heat energy generated by dropping a ball, but imagine the same situation with an asteroid coming in from outer space and crashing into the Earth's surface. That asteroid basically is disintegrated, it's obliterated, and huge amounts of heat are released. And in principle, you can do that with 100% efficiency. All the energy that's represented in that system can be converted to heat. It's the same thing with a piece of coal. You can burn a piece of coal completely away and convert that energy into heat very efficiently. But the flip side, that's converting heat into work, is more difficult. And this is true for at least three reasons. First and most simply, some of the heat that you introduce into your engine has to wind up heating the engine itself or escaping into the environment. So you're wasting some of the heat. Some of the gasoline that you pay for ends up heating up the engine. It ends up heating up the exhaust. So some of the heat energy is lost to the environment. Some of the food energy that you eat ends up just being radiated away because we radiate 100 watts, just like a light bulb. Nevertheless, you can imagine lots of different ways to make more efficient insulation, of designing more efficient engines to reduce and reduce and reduce this heat loss. So you can imagine engineering away a lot of that loss, and there's no intrinsic limit to how much of that loss you can engineer away. So you can be very, very efficient in that regard. But that's still, you're always going to lose some energy that way. Second reason, some energy is always wasted because an engine operates in a kind of cycle. For example, a piston pushes on a rod to drive the machine. Then you have to pull the piston back in order to operate it again. So you have this continuous operation, and some of the energy is going to do work, but then you have to use some energy to reset the piston so you can keep doing work again. And so there's any engine that operates in a cycle has this kind of problem. Even your heart that's pumping, it has that same kind of problem. You have to reset the heart before it can pump again. Once again, you can design an engine so that this energy loss is reduced. You can have extremely lightweight pistons, you can use good lubricants and all that sort of thing, but still you have to use some energy to reset the system. But there's a third reason, and a more subtle one, and this is the one that Carnot really hit. You can't design away this third problem. The heat energy flows through the system from a hot reservoir, the burning fuel, to the cold reservoir. That's the surroundings, that's the outside. And here's the catch. No matter how cold that outside reservoir in which the heat flows into, unless it's at absolute zero, and it can't be at absolute zero. You just can't mechanically design some system with absolute zero. Some of the energy is wasted because some of the energy that you started with is still remaining in the low temperature reservoir the heat flows out of. Because everything, even ice water, has a lot of heat energy still in it. Whatever energy you start with, it has to flow to the outside. It has to flow through your engine system. An analogy can be drawn between a heat energy and the gravitational energy of a water passing over a water wheel. And I want you to think about this analogy because it makes it a little clear. Heat's a more abstract concept, but water you can hold in your hand. So imagine designing a water wheel that's the maximum efficiency possible. The elevation of the water above sea level is analogous to the temperature of your fuel, the hot, and the level at the bottom of the water wheel is analogous to the low temperature reservoir where the water flows out. And you can imagine sea level as being zero energy, or absolute zero, if you will. So think about designing that water wheel. First, you're going to have some water leaking away, or the water is going to evaporate into the air. Or it may soak into the material of which the water wheel is made. Now you can design your water wheel with extreme efficiency so that you minimize the amount of evaporation and the amount of loss of water, the amount of leaking by sealing all the cracks very carefully. But you're always going to lose a little bit of water. There's no way around that. Second, some of the water's energy has to be used to turn the wheel. And you have buckets that are pulling down, but then you have to bring those buckets back up to a position where they can go around again. And so some of the water's energy has to be used just to raise up the buckets. Now again, you can design that water wheel to be made of extremely lightweight materials. You can have high quality lubricants so the wheel turns smoothly, but you're always going to use some of your water as the wheel goes around. And this loss is exactly like the energy used to draw the piston of a steam engine back and so forth. So there's an analogy there. But no matter how carefully you design that water wheel, it can't use the water all the way down to sea level. No matter how you design the water wheel, the water is going to spill out of the machine someplace above sea level, and then the wheel is going to move around. So some of the potential energy of the water is always wasted because the water wheel is always going to be at some level above sea level. And no matter how you design that water wheel, its efficiency is going to be limited in that way. You perhaps could design a bigger water wheel. You could perhaps design it so it gets as close to sea level as you possibly can, but there's always going to be some loss, and that's the intrinsic loss that Carnot recognized. Carnot's great contribution was the derivation of the exact mathematical law that tells us the maximum possible efficiency for any engine. That is the percentage of heat energy that can go into doing work as opposed to the percentage which is always going to be wasted just by these design considerations. Turns out that the maximum possible efficiency of any engine depends entirely on two easily measured numbers. First of all, we have T for the hot end, T of the burning fuel, T at the hot end of the reservoir. So that's the heat energy that's flowing into your system to do work. And then at the other end of the system, you have T of the cold reservoir, usually called T cold. That's the temperature of the material that flows out of the engine, the exhaust, if you will. And every power plant, every engine has an exhaust of some sort, and it's the temperature of that exhaust. An engine is just a mechanical device that's imposed between the hot reservoir and the cold reservoir. Just like a water wheel is a mechanical device imposed between high gravitational energy and lower gravitational energy. The exact analogy there. Efficiency then can be defined mathematically as the difference between these two temperatures, the difference between T hot and T cold, divided by the temperature of the hot reservoir. And to put that into a percent, you have to multiply it times 100. So here's the equation that you'd use for efficiency. Efficiency equals T hot minus T cold divided by T hot. That whole expression times 100. Now you can use this equation to calculate all sorts of efficiencies, the maximum possible efficiency for different kinds of power plants, for different kinds of engines and so forth, and this becomes very important to understand the efficiency that's possible with modern engines. For example, think about an engine in which the hot reservoir is boiling water and the cold reservoir is ice water. You just plug those temperatures, and they have to be temperatures in Kelvin, in the absolute scale of Kelvin. And here's what happens. The hot reservoir is at 373.15. The cold reservoir is at 273.15, divided by 373.15 times 100. And you can get about 27% efficiency using boiling water and boiling water and ice water. Now think about it, that's not very much efficiency. You're only using 27% of the available heat energy to do work. You can improve things if you have a higher temperature hot reservoir. So for example, if you burn coal to produce steam, and that steam could be, for example, in a typical power plant at about 550 Kelvin. So let's do the calculation again. In this case, the hot reservoir is at 550. Typically, one uses room temperature, which is about 300 Kelvin, as the cold reservoir. You divide that by 550, and you see for a coal-burning power plant, you typically can have efficiencies of 45 or 46%. That's the maximum possible for a coal-burning plant. You could design things differently. For example, you could put your coal-burning power plant in the Arctic, where the average temperature is only about 250 K in the outside air. So therefore, your cold reservoir is colder. You're stretching out the total difference temperature. And let's see what happens there. 550 minus 250 over 550 gives you almost 55% efficiency. So just by moving your power plants to the Arctic, you could gain a great deal of efficiency in a coal-burning power plant. And then think about what would happen if you have an engine in deep space. In deep space, it's possible to have, if you shield from the sun, you might have a cold reservoir as cold as 50 Kelvin. And here you really gain a lot. Do the calculation one more time. 550 minus 50 over 550 times 100. That's over 90% efficiency is possible in deep space because the cold reservoir is so cold, because that cold reservoir is getting closer to absolute zero. So in that case, you can be much more efficient. You can convert more of your heat energy into work. In Carnot's day, before these principles were understood, typical steam engines had an efficiency of only 6%. Believe it or not, 6%. But when people realized they could get much higher efficiencies and they saw Carnot's reasoning, they began to design improvements, better insulation, better materials, tighter fitting steam hoses and so forth. And today, with these improvements, efficiencies have been raised to about 40%, for example, in coal-burning power plants. That's close to 90% of the theoretical limit. So we're getting very close to the maximum theoretical efficiency of a coal-burning power plant. So here's a clear case where theoretical ideas and understanding have led to dramatic benefits for society because we use our energy more efficiently. Still, remember, 60% of the coal's energy that we burn is wasted. It just is dumped into the environment. We can't use it. Fuels can be graded according to the heat they contain. Carnot's explanation illustrates why some fuels, hot-burning fuels like coal and gas, oil, for example, are all very much valued because they burn at such high temperature. You get that bigger spread in temperature, and therefore you can have more efficient plants. About 90% of all the industrialized world's energy comes from fossil fuels. It's still possible to scrape coal off the ground in some places and to drill shallow wells. So for a time being, these fossil fuels are going to be very valuable and play a very important part in the world's energy budget. These fossil fuels represent ancient life forms that have been buried and transformed by the Earth's heat and temperature. And so they're limited resources. We are mining these out. Someday, we're going to use up the remaining store of fossil fuels. They're non-renewable resources. So we're going to have to find other sources of energy, and let's hope that they burn at high enough temperatures that we can keep that high efficiency that we now enjoy. To summarize this lecture, two great laws of thermodynamics systematize the behavior of energy. That's the capacity to exert a force over a distance. The first law says that energy can change forms many, many times, and the total amount of energy is conserved. That's the good news. But the second law places limits on how this energy can transfer from one way to another. Heat tends to spread out. It flows from hot to cold. That gives a direction in the use of energy. Similarly, an engine that converts heat to work cannot operate with 100% efficiency because some of the heat must escape into the environment, some has to be used to reinitialize the engine. These physical realities dictate how we can use energy. We can't escape the second law. But the second law goes much, much deeper than that. In the next lecture, we're going to explore one of the most fascinating, profound concepts in all science, the concept of entropy.